Right now, 4 human beings are hurtling through space at 25,000 miles per hour, farther from Earth than any person has been in 53 years, inside a capsule roughly the size of a minivan. And here is the part that nobody in the press conferences wants to linger on too long: the heat shield protecting them from being incinerated on the way home. It behaved in a way engineers did not fully predict the last time it flew. NASA looked at that, ran the numbers, held the meetings, and still said go. And the astronauts, knowing everything, got in anyway. That decision, that specific moment where informed human beings looked at incomplete knowledge and said, "We accept this," is what Artemis II actually is. Not a celebration, not a milestone press release. A formal, documented institutional bet against the universe. And by the time we finish going through what they actually accepted, the number that's going to stay with you isn't the risk percentage, it's going to be the courage. Stay with me, because this one goes places most coverage never touches. Before we get into the engineering, I want you to hold one idea in your mind throughout everything that follows. There is a difference between a mission being safe and a mission being survivable. Safe means the risks are understood and controlled. Survivable means you got through it. Those are not the same statement. The history of human spaceflight is essentially a story of survivable missions, one after another, right up until the ones that weren't. That distinction is the thread running through every single thing we're about to discuss. So let's start where this mission actually starts. Not at the launch pad, not at the countdown, but in a quiet engineering lab sometime in the weeks after November 2022. When a group of people were going through the recovered Orion capsule from Artemis Year 1 with the kind of forensic attention you only apply to hardware that is about to carry human beings. Artemis, I was unscrewed. It flew, it orbited the moon, it came back, it splashed down, the parachutes opened, NASA held a press conference about milestones and new eras. By the public metrics, it was a success. But when the engineers got up close to the recovered heat shield, they found something the thermal models had not predicted: the ablative material, a substance called Avcoat, which is engineered specifically to burn away in a controlled, predictable manner during re-entry, absorbing heat rather than conducting it inward, had not behaved the way the simulation said it would. There were pockets of erosion deeper than expected. More specifically, gas had become trapped inside the Avcoat material during either the manufacturing process or the re-entry heating cycle itself. And those trapped gas pockets had created localized pressure points inside the material, and that internal pressure had caused cracking, and that cracking had caused what engineers call spallation, pieces of the heat shield physically breaking off during the highest thermal stress moment of the entire mission. Now I want to be precise here, because the competitor space, the YouTube ecosystem around this topic, has gotten this wrong in ways that are worth correcting. They did not fly the same cracked heat shield. They built a new one. What they kept was the same design, the same material, the same fundamental architecture. And the reason that matters is because the spallation was not a one-time defect in a particular unit. It was a behavior of the material under real re-entry conditions at Orion scale, conditions that the models had not fully captured. So building a new heat shield from the same design does not eliminate the underlying question. It just means you have a fresh version of a system whose edge case behavior is not completely characterized. Think about what spallation actually means physically. During re-entry, the heat shield is doing its job by burning. That's intentional. Avcoat is designed to ablate, to sacrifice itself in a controlled way. Outer layers burning, new layers exposed, thermal energy carried away from the capsule rather than into it. It's an elegant system, and it's worked on every American crewed capsule re-entry in history. But spallation is not controlled burning. Spallation is uncontrolled fracture. Pieces departing the surface not as part of the designed ablation process, but because internal mechanical failure pushed them off. And those pieces, once separated, do not float harmlessly away. They are carried by the hypersonic flow around the capsule. Depending on trajectory, they can travel backward in the aerodynamic wake toward the parachute compartment, the same compartment that contains the only system capable of slowing the capsule from terminal velocity to a splashdown speed the crew can survive. Debris from a spalling heat shield impacting a parachute before deployment is a failure cascade with no recovery path. So what did NASA do? They modified the re-entry trajectory. Specifically, they steepened the descent angle slightly. The logic is elegant in the way engineering solutions often are. A steeper angle means the capsule gets through peak heating faster, less time at maximum thermal stress, lower cumulative heat absorption during the most dangerous portion of the re-entry profile, reduced probability of the spallation behavior expressing itself at dangerous levels. Completely reasonable. Except, and here is the thing that most coverage glosses over, because it requires you to hold two ideas simultaneously. A steeper descent angle reduces the duration of peak thermal exposure, but it increases the instantaneous intensity. You are compressing the same thermal event into a shorter window, which means the peak rate of temperature change, the peak heating flux the material experiences in any given second, is actually higher than it would have been on the original trajectory. You traded duration for intensity. You moved the risk. You did not remove it. And the bolts, the fasteners holding the heat shield assembly to the capsule structure, also experienced thermal conditions beyond their design specification on Artemis I. That detail got considerably less public attention than the spallation. But fastener failure under hypersonic aerodynamic loading during peak reentry heating is not a local problem. A heat shield that begins to separate from the capsule structure at 5,000 degrees Fahrenheit is not a recoverable situation. So let's inventory what we're working with before we move forward, because I want you to hold this clearly. You have a heat shield whose ablative material demonstrated unexpected fracture behavior during its only test flight. You have a fastening system that experienced conditions beyond design specification on the same test flight. You have a trajectory modification that reduces the duration of peak thermal exposure while increasing instantaneous peak stress on the same material. And you have 4 human beings inside the spacecraft. That is, by the formal determination of the most rigorous aerospace engineers on the planet, within acceptable risk parameters. Every single one of those things is simultaneously true. And the question that should sit at the back of your mind, not as panic, but as the right kind of intellectual discomfort, is this. What is the difference between a risk that has been bounded and assigned a probability and a risk that has simply been made to look smaller than it is? I'm not saying Artemis II is unsafe. I'm saying that question deserves to be asked out loud, and I'm curious whether you think NASA answered it correctly. Drop your honest take in the comments. I genuinely want to know. Now, NASA's internal crew loss probability threshold for this mission has been described in documentation as approximately 1 in 30. Before that number lands wrong, it needs context. The early space shuttle missions had retrospectively estimated crew loss probabilities closer to 1 in 9. 1 in 30 is dramatically safer than that. By the standards of human spaceflight history, 1 in 30 is genuinely conservative and represents an enormous amount of engineering rigor and institutional caution. But let's sit with what 1 in 30 actually means in human terms. If you imagine 30 different crews flying 30 identical Artemis II missions, the statistical expectation is that one of those missions does not bring everyone home. Not because anyone was careless. Not because anyone cut corners, but because the environment is genuinely hostile and the knowledge is genuinely incomplete and probability is real. That number is simultaneously the most honest thing NASA has ever published about a mission and the most unsettling, uncomfortable and acceptable at the same time. Both true simultaneously. There is a system at the tip of the Orion spacecraft that generates approximately 400,000 pounds of thrust in under 3 seconds. For context, a fully loaded Boeing 747 at maximum takeoff power across all 4 engines produces roughly 240,000 pounds of thrust total. The launch abort system produces nearly double that from a single solid rocket motor, shorter than a city bus. Its entire purpose is to rip the crew capsule away from an exploding rocket faster than a human being can consciously register that an explosion is happening. It is automated. It monitors booster performance through sensors and detection algorithms, and if it registers a signature consistent with catastrophic failure, it fires. No human in the loop, no confirmation requests. The decision is made by software in milliseconds, and the crew is pulled away at up to 15 times the force of gravity. For a brief reference, fighter pilots train for years to maintain consciousness at 7 to 9 G. The launch abort system applies 15 G involuntarily without warm-up to 4 people who may have had no advanced sensation that anything was about to happen. The system is genuinely impressive and genuinely validated, and it contains within its design a category of failure modes that would not exist if it weren't there. This is one of the more counterintuitive truths of complex safety engineering. Safety systems do not reduce the total number of ways a mission can fail. They change the distribution of failure modes. They close some pathways, and by the act of existing as additional complex hardware in the system, they open others. Walk through the full picture with me. If the abort system triggers correctly during an actual booster failure, the crew survives. Mission lost, crew alive. If it triggers falsely, sensor error, software glitch, vibration signature from a perfectly functional booster that happens to match the failure signature, the crew is pulled away from a rocket that was working. Mission over, crew alive, survivable. If it fails to trigger during an actual catastrophic event, sensors miss it, or the ignition system has a hardware failure at the exact wrong moment, the crew is inside a structurally failing vehicle with no escape path. And then there is the fourth scenario, the one that lives in the philosophically uncomfortable corners. The abort system fires correctly. Everything works as designed. The motor ignites 15 G, crew pull clear. The capsule reaches its peakable altitude, and then the jettison motor, the secondary motor that separates the abort tower from the crew capsule so the parachutes can deploy, fails to fire. The tower stays attached. It is sitting directly above the parachute compartment. The parachutes cannot deploy through a solid rocket motor. The crew successfully escaped the exploding booster. The crew is now falling toward Earth with no functional parachute system. The launch abort system saved them from the explosion and created a different unsurvivable outcome. None of these scenarios is likely individually. The point is not to suggest the system is poorly designed. The point is something more important. When you build a safety system, you are not making the mission safer in an absolute sense. You are making it safer in a probabilistic sense within the specific failure domain the system addresses, while simultaneously introducing failure pathways that would not exist without it. This is why redundancy improves survival probability in anticipated scenarios and expands total system complexity simultaneously. And complexity is where unexpected failures live, not in the modes that were anticipated and designed around. In the interactions between components, the edge cases, the scenarios no one modeled because they sat outside the imagination of the design team. There is no lifeboat on Artemis II. I want to sit with that because it is genuinely underappreciated in almost every piece of coverage this mission has received. We have spent 25 years operating the International Space Station, and in that time the presence of a rescue vehicle has become so normalized as part of the crude spaceflight architecture that its absence registers as almost an oversight rather than a deliberate design reality. At any given moment on the station, there is at least one Soyuz or Crew Dragon docked and ready to undock and return the crew to Earth. The transit is ours. The capability is real. Apollo 13 had a lifeboat too, though it was never designed to be one. The lunar module was built to land 2 astronauts on the surface and return them to the command module waiting in orbit. It was not built to be a survival vehicle for 3 people on a 4-day emergency transit home. Its carbon dioxide scrubbing system was not sized for 3. Its power budget wasn't designed for extended emergency operation. Its guidance wasn't configured for the burns that needed to happen. None of that mattered in the end because it was there. It existed. The mission architecture had included a second vehicle with its own independent power, its own propulsion, its own life support. When the service module exploded and the command module became uninhabitable, the crew had somewhere else to go. They improvised carbon dioxide scrubbers out of plastic bags and cardboard and tape. They powered down every non-essential system. They came home. The lunar module was not supposed to be a lifeboat. It became one because it was there. Artemis II does not have a second vehicle. There is no tunnel to crawl through, no independent hull, no backup propulsion sitting on a different spacecraft that can be pressed into emergency service. There is one spacecraft, 4 astronauts, and a trajectory defined by orbital mechanics. The free return trajectory is genuinely elegant physics and worth understanding precisely because it is so often misrepresented. If the main propulsion system fails after the burn that commits the spacecraft to its lunar path, the geometry of Earth's and the Moon's gravity fields will arc the spacecraft back toward Earth without any additional thrust required. Gravity does the work. Isaac Newton in the 17th century worked out the mathematics that make this possible, and those mathematics are as reliable as anything in physics. In that specific narrow sense, the free return is a real safety feature. But a return mechanism is not a rescue system. The distinction matters enormously. A rescue system adapts to your situation. It gives you options. A return mechanism does one thing. It brings you back toward Earth. It does that one thing regardless of whether the spacecraft is in a condition to survive arrival when it gets there. If the heat shield is damaged, if the parachute system has a fault, if the power systems have degraded to where the guidance computers cannot execute the entry sequence correctly, the free return brings you back to Earth in all of those scenarios and helps you survive none of them. What Artemis II replaced rescue capability with is deterministic orbital mechanics. After the translunar injection burn, physics is not a backup system. Physics is the only system, and physics cannot be rebooted, upgraded mid-mission, or called in from Houston when the situation changes. The European Space Agency built the service module that provides propulsion, oxygen, power, and thermal regulation for the Orion spacecraft. ESA's engineering is by every credible measure excellent, and nothing I'm about to say is a criticism of the hardware or the people who built it. It is an observation about architecture. The service module is a single consolidated unit providing multiple critical functions that on Apollo were distributed across two separate vehicles with independent systems. The four main engines provide thrust for every significant burn. The solar arrays generate essentially all electrical power beyond battery reserves. The thermal control system regulates the temperature environment, keeping the crew alive and electronics functional. The oxygen tanks supplement cabin atmosphere. In systems engineering, this is called functional consolidation, and it has real advantages. Lighter than a redundant distributed system. Simpler to operate. Narrower integration test scope. For a multi-day flyby mission, it makes engineering sense. The trade is failure tolerance. On a consolidated system, a failure in any critical function doesn't stay local. It propagates. A propulsion failure is a trajectory failure because the burns defining the return path cannot execute. A power failure is simultaneously a life support failure, a guidance failure, and a communications failure because all of those systems draw from the same source. A thermal control failure compounds into every other system because electronics that overheat fail, and failing electronics take other systems with them. Apollo's architecture was almost extravagant in its redundancy by comparison. Two vehicles each with independent power, multiple redundant guidance computers, fuel cells and batteries, systems designed to continue operating after losing significant portions of capacity. The mass cost was real, but the failure tolerance was correspondingly generous. You could lose quite a lot of Apollo and still have a path home. Apollo 13 demonstrated that in the most vivid way possible. Artemis II is leaner, more efficient, more capable in many technical respects, but it handles one specific category of failure least gracefully, not the catastrophic instantaneous ones, the explosion, the sudden hull breach, the slow compounding systemic ones. A propulsion system delivering 92% of nominal instead of 100, a power system losing capacity gradually, a thermal anomaly reading within tolerance on day 1 and outside tolerance on day 3, each one as it develops, reduces the options available for managing the ones that follow. For approximately 45 minutes during the Artemis II mission, the Moon will be directly between the crew and Earth. Every radio signal mission control sends travels in a straight line at the speed of light. Radio waves do not bend around planetary bodies. The Moon is 3,474 kilometers in diameter, with nothing between its surface and hard vacuum. When the spacecraft passes behind it, the electromagnetic connection between the crew and every human being on Earth is not degraded or weakened. It is physically interrupted. Gone. Mission control cannot hear them, cannot see their telemetry, cannot send commands, cannot warn them, cannot help them. The most sophisticated ground support infrastructure in human history becomes, for 45 minutes, a collection of very expensive antennas pointing at a rock. Only 27 humans have ever experienced what that actually feels like from inside. All of them flew on Apollo missions in a compressed window of history that ended in December 1972. Michael Collins, orbiting above the lunar surface during Apollo 11 while Armstrong and Aldrin were below, described it as the most profound solitude he had ever experienced, and he was separated from the nearest other humans by only a few hundred kilometers. The Artemis II crew will have 384,000 kilometers of empty space between themselves and the nearest other human being, with the Moon blocking the view. Their accounts across different missions and different crews are remarkably consistent in one way. Every one of them describes the experience as something that does not map onto prior human experience. Not frightening in the way fear of a specific danger is frightening. Not lonely in the way ordinary loneliness is lonely. Something that the existing vocabulary of human emotional experience was not quite built to describe, because the experience itself has no terrestrial equivalent. For 45 minutes, the only things that exist in the perceptual universe are the Moon filling one window, the stars filling every other direction, and the four of you in a capsule the size of a minivan. The Artemis II crew will be the first humans to experience that in over 50 years. And I find myself genuinely wondering what they will say about it when they're back, what words they will reach for, whether the 50 years of distance from the Apollo accounts will produce a different language for the same experience, or whether they will reach the same conclusion Collins did, that some things simply resist being put into words because the words evolved to describe a different category of experience entirely. But here's the thing I want to be careful about. The psychological dimension of the far side blackout, while genuinely fascinating, is not the operational problem. The operational problem is this. During those 45 minutes, the crew of Artemis II will not be resting. They will not be floating peacefully watching stars and contemplating the human condition. They will be working. The far side passage is not a pause in the mission. It is a continuation of it, with all the same operational demands and system monitoring requirements, now occurring in a context where the entire collaborative support structure that makes mission control valuable has been removed from the equation. Navigation assessments may occur during this window. System checks continue regardless of communication status. Potential burn preparations require crew attention. If anything goes wrong during those 45 minutes, any anomaly, any system alert, any unexpected behavior anywhere in the spacecraft, mission control will not know about it in real time. They will find out approximately 45 minutes later when telemetry reestablishes. Whatever was happening will have been developing undetected from the outside for the full duration of the blackout. To understand how long 45 minutes actually is in this context, think about the most famous emergency in spaceflight history. The explosion that crippled Apollo 13 occurred at 55 hours and 54 minutes into the mission. The crew heard a bang, felt the spacecraft shudder, and within seconds, not minutes, Lovell was talking to Houston. Within seconds, mission control could see the oxygen pressure dropping in real time. They could watch the power systems degrading. They could work the problem collaboratively before the full scope of the emergency had finished developing. Every decision that saved those three people was made in a context of continuous information flow between the spacecraft and the ground. The improvised carbon dioxide scrubbers, the power down sequence, the trajectory burns, all of it required the ground and the crew in constant contact, sharing data, building a picture together, responding as it changed. On Artemis II, during the far side passage, that loop does not exist. The crew is operationally autonomous in a way that has no peacetime equivalent for any other profession on Earth. Whatever happens, happens. Whatever decision gets made by 4 people with the training they brought with them, the data their own instruments can provide, and nothing else. The question I want you to think about and drop in the comments is this. If you were one of those 4 astronauts and you knew about the blackout, the heat shield, the radiation environment, everything we're discussing, would you have gotten in? I'm not asking what you think they should have done. I'm asking what you would have done, because I think the answer tells you something interesting about yourself. In August 1972, the Sun did something that almost changed the history of space exploration entirely. A coronal mass ejection of extraordinary intensity sent a wave of high-energy protons streaming through the inner solar system. These were not routine elevated readings that standard solar monitoring flags as manageable. They were protons accelerated to a significant fraction of the speed of light, carrying enough energy to penetrate aluminum spacecraft walls and deposit meaningful radiation doses in biological tissue within hours. Analyses of what an Apollo crew would have received if they had been in transit between Earth and the Moon during the peak of that event range from acute radiation sickness to potentially lethal doses for at least some crew members without intervention. The shielding on an Apollo command module was designed for routine cosmic ray exposure and moderate solar particle events. It was not designed to stop August 1972. Nothing that could realistically fly to the Moon in that era was. The event happened between Apollo 16 and Apollo 17. Apollo 16 splashed down in April. Apollo 17 launched in December. The solar storm hit in August. The gap between an active Apollo crew and a solar particle event that might have killed them was 45 days. Not a comfortable engineering margin, a timing coincidence. The fact that no crew was in cislunar space during that event is not the result of careful solar weather planning. It is the result of the mission schedule happening to land on the right side of a random natural event. Artemis II is launching near the peak of solar cycle 25. The crew has access to a designated radiation shelter inside the capsule. It is not a separate, heavily shielded room. It is a defined area where the crew can position themselves to maximize the amount of spacecraft material between themselves and incoming particle flux, using food and water stores, equipment stowage, everything available as additional shielding. It provides meaningful dose reduction. It is not a guarantee. It is a mitigation. Mission Control monitors solar activity continuously through space weather observatories and can issue warnings when elevated particle flux is detected. If a solar particle event begins while the crew is on the near side of the Moon, with communication intact, Mission Control warns them. They move to the shelter position, they manage the dose. But here is the scenario that sits at the intersection of two separate vulnerabilities and produces something more troubling than either individually. If a major solar particle event begins while the crew is behind the Moon, if the onset of the storm falls inside the 45-minute blackout window, Mission Control cannot warn them. The warning system, the monitoring infrastructure, the real-time solar weather tracking, all of it is irrelevant because the communication link is down. The information exists on Earth. The warning would be sent immediately if the link were active. The crew has no way to receive it, and the most dangerous solar particle events have a characteristic temporal structure that makes response time critical. The highest energy particles arrive first as a relatively brief precursor to the main body of the particle wave. That precursor is the warning. Recognize it quickly and you have some lead time before the bulk of the dose arrives. That lead time is measured in minutes. If the crew is in the middle of a navigation assessment or troubleshooting a different system at the moment the radiation monitors start registering anomalous readings, if no one is watching that specific display at that specific second, the response time compresses, the precursor passes, the main event arrives. Radiation is the most philosophically unsettling hazard in the space environment, and I want to take a moment to explain why, because it is not just about the biological danger. It is about the complete mismatch between the nature of the threat and the sensory equipment human beings evolved to detect threats. Every physical danger that shaped human evolution over millions of years announced itself through the senses. Fire is visible and hot. A predator makes sound and movement. A fall has sensation. Even chemical hazards in natural environments tend to have smell or taste as warning signals. Human biology is exquisitely tuned to detect and respond to threats that interact with the physical world in ways that produce sensory information. Ionizing radiation produces none. You cannot see it, cannot hear it, cannot feel it, cannot smell it. There is no sensation of warmth, no tingling, no proprioceptive signal that anything is happening. High-energy protons from a solar particle event pass through spacecraft walls, through the crew's bodies, through everything in the capsule at a significant fraction of the speed of light, depositing energy in biological tissue through ionization interactions completely below the threshold of human sensory detection. The first indication that something significant happened might be nausea hours later, fatigue, the beginning of symptoms that won't fully manifest for days. The crew cannot look out the window and assess the radiation environment. They cannot develop intuition about it from experience. It is invisible. It is silent. It is physically indifferent to the fact that 4 human beings are trying to manage it, and the only interface between the crew and any knowledge of what the radiation environment is doing is the readout on an instrument display that requires someone to be actively looking at it at the right moment. At 25,000 miles per hour, the Orion spacecraft approaching Earth for re-entry must enter the atmosphere within an angle between 5.5 and 7 degrees relative to the local horizon, shallower than 5.5 degrees, and at that speed the capsule skips off the upper atmosphere, the way a flat stone skips across water. The atmospheric density at that altitude is so low that instead of decelerating the capsule, it deflects it. The spacecraft bounces back into space on a modified trajectory, potentially in the wrong ocean, potentially on a path that doesn't return to Earth within a useful time frame with the crew running out of consumables. Steeper than 7 degrees, and the aerodynamic loads and heating rates exceed what the structure was designed to survive. The heat shield, the one that already exhibited spallation, encounters a thermal environment more extreme than its design envelope. The spacecraft does not make it through re-entry intact. Between those two outcomes there is a window of 1.5 degrees. Extend your arm fully in front of you and look at your little finger. The apparent width of your little finger at arm's length subtends approximately 1 degree of visual angle for a typical adult. Your entry window for Artemis II is 1.5 times the apparent width of your little finger held at arm's length, and you are trying to thread that window from approximately 250,000 miles away, traveling at 10 times the speed of a rifle bullet. with a trajectory that has been accumulating any navigation errors that occurred during the transit. Under nominal conditions, the guidance computer manages this. The Orion spacecraft's guidance, navigation, and control system is considerably more sophisticated than anything that flew on Apollo, and the algorithms running it represent decades of accumulated expertise in spacecraft guidance. But the guidance computer is an electronic system, and high-energy protons from the solar environment, the same particles posing biological risk to the crew, also pose a risk to electronics. When a high-energy particle passes through a semiconductor memory chip, it can deposit enough charge to spontaneously flip a stored bit from a 0 to a 1, or a 1 to a 0. Modern radiation-hardened electronics use error detection and correction codes, additional redundant bits that allow the computer to identify when a bit has flipped and correct it without corrupting a calculation. The system works well for the vast majority of events. But bit flips in critical navigation calculations, particularly in the memory locations holding the values defining the entry corridor parameters, can potentially translate into trajectory decisions with physical consequences. A guidance computer that believes it is targeting a 6-degree entry angle when it is actually targeting 4.5, will fly a trajectory that skips off the atmosphere. The backup to a corrupted guidance computer is, at its core, the same system Apollo crews used, and that navigators used for centuries before the space age. Star navigation. The crew can use an optical device to measure the angular positions of known stars relative to the spacecraft's attitude and Earth's limb, calculate precise orientation and trajectory from those measurements, and use that calculation to correct re-entry targeting. The mathematics are sound. The technique works. It worked on Apollo. But it requires time and cognitive clarity. If the failure event that degraded the guidance computer was a severe solar particle event, and the crew has been receiving radiation exposure during the same window, the question of their cognitive status at the moment they need to perform emergency manual navigation becomes a real operational question. In the most extreme scenario imaginable, guidance computer corrupted, crew managing radiation exposure, communication blackout in effect, re-entry window approaching. The most sophisticated crewed spacecraft ever built falls back to a human being with an optical instrument measuring the angle between a star and Earth's horizon, doing mathematics that maritime navigators did with sextants on wooden ships crossing unknown oceans. That is not a design failure. That is the physics of the problem. Irreducible and non-negotiable. Under conditions of extreme system failure, complexity collapses. The layers of redundancy and automation peel back one by one, and underneath them you find the same irreducible challenge that has always been at the center of navigation: a human being, an instrument, and the geometry of the sky. These are not independent risks sitting in separate compartments of the mission profile. They're connected through the spacecraft and the people inside it, the heat shield uncertainty, the service module's consolidated dependency, the communication blackout, the solar maximum radiation environment, the biological risk to the crew, the operational risk to the guidance electronics, the 1.5-degree entry corridor. Each degradation of the shared substrate of spacecraft and human beings affects the crew's ability to manage everything else. This is what engineers mean when they talk about risk stacking, not just the accumulation of individual probabilities, but the coupling of failure modes through shared systems and shared human capacity. In a coupled system, failures create conditions that make subsequent failures more likely. Space is not empty. The mental image most people carry of the space between Earth and the Moon is essentially one of pure featureless void. The reality is considerably more crowded and considerably more dangerous in a way that operates below the threshold of human perception and entirely outside the reach of human response. The cislunar environment is an active debris field, not in the cinematic sense of visible rocks tumbling dramatically through darkness, but in the physical sense of a volume of space populated by particles ranging from microns to meters in diameter, moving at velocities that are the accumulated result of billions of years of solar system dynamics. Impact velocities for objects in cislunar space range from roughly 3 km per second on the low end to approximately 70 km per second on the most energetically unfavorable. Trajectories. A 9mm pistol bullet, roughly the fastest projectile most people have any intuitive reference for, leaves the muzzle at about 370 meters per second. The lower bound of micrometeorite impact velocity in space is 8 times faster than that bullet. The upper bound is nearly 200 times faster. You are not dealing with faster bullets. You are dealing with a different physical category of impact event entirely. At those velocities, mass stops behaving the way it does in any terrestrial impact scenario. Kinetic energy scales with the square of velocity, which means doubling speed quadruples energy. A particle the size of a grain of sand arriving at 40 kilometers per second carries kinetic energy roughly comparable to a rifle round. A particle the size of a small marble at the same velocity delivers energy comparable to a hand grenade. These are not metaphors chosen for effect. They are the actual physics of what happens when small fast objects meet spacecraft hulls. The Orion capsule is shielded against micrometeorite impacts. A Whipple shield design, named after astronomer Fred Whipple, who proposed the concept in 1947, where a thin outer bumper plate vaporizes or fragments an incoming particle and spreads its energy across a wider area before it can reach the primary pressure hull. The shielding was designed to protect against the statistical distribution of most likely impact events. It worked well for that population. It was not designed to stop everything, because designing a spacecraft hull to stop everything the cislunar environment could theoretically deliver would require so much shielding mass that the spacecraft would be too heavy to launch. At some point in the optimization, you accept the residual risk of the impacts you cannot realistically shield against, because the alternative is not flying at all. The probability of a mission-ending micrometeorite strike during Artemis II is low. That statement is accurate, and it is in a very specific sense beside the point. The universe does not consult probability tables before deciding where a given particle is on a given day. Low probability is a statement about a population of events. The crew of Artemis II is not a population. They are 4 individuals, and for them any given impact either happens or it does not, and the probability that preceded it is irrelevant once the particle is in flight. The Orion capsule does not glide to a landing. It does not have wings or a runway. After re-entry, after the heat shield has done its work, the capsule falls. The parachute system deploys in a carefully sequenced cascade. Drogue shoots first to stabilize attitude and begin deceleration. Then 3 main parachutes, large enough that their combined canopy area covers roughly the footprint of a small office building. Slowing the descent to a splashdown speed, the capsule structure and crew can survive. 2 of 3 main parachutes must function. That is the threshold. 1 failure is within the system's design tolerance. 2 failures are not tolerable, and here is the connection that most analysis misses. The deployment conditions, the altitude, the velocity, the capsule's pitch angle, the aerodynamic loads at the moment of deployment are not independent of earlier decisions. The trajectory modification NASA implemented to reduce the heat shield's thermal exposure changes the capsule's energy state at re-entry. A different energy state means a different velocity profile through the atmosphere. A different velocity profile means the capsule arrives at parachute deployment altitude in a slightly different condition than the nominal mission design assumed. The parachutes were tested and validated against nominal conditions. The actual conditions will be the modified ones. None of this means the parachutes will fail. It means the conditions they are deploying into are not identical to the conditions they were primarily validated against, because the conditions upstream were changed to manage a different risk. The risks are coupled. Changing one changes the environment faced by the others. And then there is the scenario that does not involve any catastrophic failure at all. No explosion, no micrometeorite, no parachute malfunction. Just a burn that delivers slightly less than nominal thrust. A trajectory that diverges from the planned path by a fraction of a degree. Too small for initial telemetry to flag as critical, accumulating over distance into a divergence that becomes significant only when it is too late to correct with the propellant budget remaining. If the main engine underperforms during the critical return burn, not fails completely, which would trigger immediate emergency protocols, but delivers 94 or 95% of nominal thrust over a burn slightly longer than planned, the trajectory geometry shifts. The spacecraft arrives at the Moon's gravitational sphere of influence on a slightly different vector than intended. And instead of the free return geometry curving it back toward Earth, the Moon's gravity catches it. The spacecraft enters an elliptical orbit around the Moon, not falling toward Earth, falling around the Moon in a closed orbit going nowhere. The crew would know immediately. Telemetry would be unambiguous. Communication would be intact. Mission control and the crew would have a complete shared picture of what happened and what it meant. They would work the problem together with every resource NASA's engineering infrastructure could bring to bear, and at the end of that process they would arrive at a number, the delta V required to break out of lunar capture orbit and set a course for Earth. They would compare that number to the propellant remaining after the underperforming burn, and if the numbers did not match, if the physics required more energy than the spacecraft had remaining to provide, the engineering options would be exhausted. Earth would be visible through the capsule windows, a blue-white sphere roughly the size of a marble held at arm's length, approximately 384,000 kilometers away. A radio signal crosses that distance in 1.3 seconds. The crew could talk to their families, they could talk to mission control, they could see with their own eyes the planet they came from and the planet they were trying to return to. And the orbital mechanics would be indifferent to all of it. Proximity does not equal accessibility in space. You cannot negotiate with the gravitational field. You cannot improvise your way out of a propellant deficit. Earth would be right there, visible and radio reachable, and completely physically unreachable. And the gap between those two facts would be the whole story of what it means to be a human being in deep space with insufficient delta V. That scenario. Quiet. Slow. Technically understood, survivable in its initiation and unsolvable in its conclusion, is the one that most cleanly illustrates what Artemis II actually accepted. Not the fire, not the impact, the math. In 1969, when Apollo 11 returned and splashed down in the Pacific Ocean, 3 of the most celebrated human beings on the planet were immediately placed in a modified Airstream trailer and told they could not leave. For 21 days, Neil Armstrong, Buzz Aldrin and Michael Collins lived in a converted mobile quarantine facility, a sealed pressurized trailer with small windows and limited space docked to the side of the recovery ship. Scientists monitored them for any sign that they had brought something back that Earth was not prepared for. The quarantine protocol was not based on evidence. Nobody had found lunar microorganisms. Nobody had a specific threat model for what a lunar pathogen would look like. The protocol was based on something more fundamental. The probability of something harmful existing in the lunar environment was not precisely zero. The consequences of being wrong were significant enough to justify an expensive, logistically complicated precaution against a threat that almost certainly did not exist. That is a very specific kind of thinking. Not the thinking of someone who modeled the risk and found it acceptable. The thinking of someone who looked at the edge of the unknown and decided that the cost of caution was lower than the cost of being wrong in a domain where being wrong cannot be undone. NASA ended the lunar quarantine after Apollo 14. 3 missions, 6 astronauts on the surface, nothing concerning found. The probability assessment shifted from unknowable to effectively negligible, and the precaution was removed. This is how institutional risk assessment is supposed to work. You begin with wide uncertainty. Experience narrows it. The margin shrinks. The precaution relaxes proportionally. The system gets safer as the knowledge base expands. But it works beautifully when the risks you are accumulating experience with are the same risks you will face on subsequent missions. When the threat model is stable, when the domain of the unknown does not expand faster than the domain of the known. The heat shield spallation is not a risk that accumulated experience characterized into predictability. It is a risk that appeared during the only test flight and was managed through trajectory modification rather than resolved through redesign. The uncertainty was bounded, given a shape, assigned a probability, and accepted. Bounded and resolved are different things. Here is the question I keep returning to, and I genuinely want to know your answer in the comments. There is a concept in aviation safety called normalization of deviance. It describes the process by which something that should be alarming becomes, through repeated exposure, unremarkable. The engineers at Morton Tire Co. warned about O-ring erosion before Challenger. Multiple shuttle flights had experienced O-ring erosion and landed safely. The gap between concerning and catastrophic had been crossed so many times without disaster that the distance seemed permanent. It wasn't. The foam strike risk that destroyed Columbia was similarly known, assessed, discussed, and normalized over the course of dozens of successful missions into something that felt like a managed quirk rather than an existential threat. Artemis II, if it returns safely, will begin the normalization of its specific risk profile. The spooled heat shield, managed through trajectory modification, will become an established precedent. The 1 in 30 crew loss probability will become the baseline from which subsequent missions are assessed. The 45-minute communication blackout will become routine operational territory. The service module's consolidated architecture will be carried forward into missions with longer durations and higher demands. None of that is inevitable. The normalization process can be interrupted by rigorous, sustained, institutionally supported attention to the distinction between survivable and safe. NASA knows this. The engineers who made the Artemis II risk assessments know this. The culture of modern spaceflight is in many ways more conscious of normalization risk than the shuttle-era culture was. But consciousness of a risk is not immunity to it, and the pressure to move forward, the schedule pressure, the budget pressure, the political pressure to demonstrate progress in human space exploration is as real for Artemis as it ever was for Shuttle. Maybe more real given the international commitments and commercial partnerships and explicitly stated ambitions of the program. The 4 astronauts out there right now know all of this, not abstractly, the way a person who has read about it knows it, but operationally, in the procedures they have memorized, the failure scenarios they have simulated, the risk assessments they've reviewed and signed off on and chosen to proceed with anyway. Reed Wiseman, Victor Glover, Christina Koch, Jeremy Hansen. They accepted not just the specific enumerated risks, but the condition underlying all of them, the fundamental condition of being human in a universe that was not arranged for human convenience. They are out there because the species they belong to has been asking a question for as long as it has been capable of asking questions. What is out there? And the answers that have come back from the places we have managed to reach have consistently been variations on the same theme. It is extraordinary. It is indifferent. It will kill you if you make a mistake, and possibly if you don't. And it is worth going anyway.